that have all been successful in last year's model coding competition. For example, there are knowledge combination-based solvers like D4, there are component caching solvers like SharpSubTD, there are dynamic programming solvers like BPMC, and there are also solvers employing approximate methods like ApproximC. And so into this magnitude of approaches, we have sort of a new idea, and it's this idea is due to Raymond Mock and Turner from the physics community. So but first, some people from the physics community noticed that you can use these tensor networks for that. And a few years later, there was also a paper stating that you can use them for model counting. So what's a tensor network? Basically, a tensor is a generalization of a vector or a matrix. So a vector has one axis, and a matrix has two axes, but a tensor can have an arbitrary number of axes, so 0 or more. So I have written the three tensors here, and I've labeled the axes with X, Y, and Z. And these entries are in general numbers. In our case, they are natural numbers. And a set of tensors that have some axes in common is called a tensor network. And in such a tensor network, there are a number of operations. So one operation that's important today is full combination, which yields again a tensor. And it's kind of a product of the input tensors. So for every location in the new tensor, the new tensor has all the axes from any tensor in the original tensor network. And every location has an entry which is a product of corresponding entries in the original tensors. So for example, here is the entry at X, Y, and Z all equal to 0. And that's the product of those three corresponding entries. So it's 0 in this case. And this entry is a 1 because it's the product of these corresponding entries, which are 1. And if we can compute the full contraction, if we can compute the full combination, we can compute the full contraction, which is just defined as the sum of the entries in the full combination. So in this example tensor, the full contraction would be 3.
May I ask a question?
Yeah.
Is it related to the permanent?
Oh, I'm not really sure. I don't think I can answer this. But you can use these tensor networks for model counting by using input tensors that represent our clauses and kind of act as a truth table for these clauses. So, for example, we have a unit clause not X. And this is 1 if X is 0, and 0 if X is 1. So then we have these other clauses that each have 1, 0 entry, and the rest are 1s. And so these input tensors represent our clauses. And the full combination of these tensors is the truth table for the CNF. Because the truth value of the CNF is the end of the truth value of the clauses, and the entry of the tensor is a product, which in our case is the same at the end of these individual values. So in this full combination tensor, we get the truth table of our CNF. And if we can compute the full contraction, which is just the sum of these entries, then we get the model count. Now, we defined the full contraction via the full combination, but that's in general an efficient way and inefficient way to compute it. Because if we have a big tensor network with many axes, then the full combination will be a really big tensor with its number of entries is 2 to the power of number of x's. So to reduce the computational workload, we always sum up the x's as early as possible. So, for example, if we want to compute the full contraction of the tensor network, and we start with 2 of the tensors that has the axis x, and compute their combination, which is this tensor. And then what we can do is we can sum up the values with x equals 0 and x equals 1 to get this tensor, which no longer has an axis x. And this tensor can then be combined with the third tensor. And we again compute the combination. And in the end, we aggregate over the y-axis to get this tensor, and then we aggregate on the z-axis and get the same result. But especially if you have a big tensor network, this really saves a lot of computations. So the algorithm in general does this by determining a contraction order, which is just the permutation of the axis. And then it loops over these axes. And for each axis, it will recombine all the tensors that contain this axis. So in our example, it would be, for example, the axis x, and we combine all these tensors. And then we aggregate over these axes and remove it. And then we go to the next axis and do this for all the axes. And in the end, there will be no axis left. So we have a tensor with 0 axis, which is just a number, which is our model count. So this gives us a model counting solver. We just take our input clauses and convert them to tensors, and then we compute the full contraction according to this algorithm, which is well known in the tensor community. Now, an advantage is that these tensor operations are well optimized, and they are fast also on current hardware. But we want to know how powerful this approach is precisely, and how expressive is it, are there any limitations? And for this, in order to answer this, we want to use proof complexity. So both in SAT and in SharpSat, we have the situation that proof systems can correspond to solver performance. And ideally, they can characterize the strengths of solvers. So there's a well-known correspondence in the SAT case between CDCA and resolution, which is not completely precise for practical resolution, but it's a really helpful approach to characterize the strength of a solver using such a proof system. And there are some existing proof systems for SharpSat. So we know of KCPS, of MICE, which we are using. So it was originally introduced at SAT 2 years ago, but we are using the simplified version from SAT 1 year ago. And there's also the CPOC system. And I want to explain a little bit about MICE systems because it's a line-based proof system. The lines are called claims. And these claims consist of a formula, a partial assignment, and a model count. And such a claim represents the fact that a partial formula F under the partial assignment A has exactly C models. So we have these 3 proof systems, but none of these really tightly correspond to our tensor solvers. So we built a proof system that does precisely that captures the strengths of this tensor-based solver. And it's again a rule-based proof system, and its lines are just these tensors. And just like in the solver, we have a step for combining two tensors, and we have a step for aggregating of an axis, and we have some restrictions to make it all sound and make it all work out. And the proof size is not the number of steps in the proof because these tensors can get really big. So as proof size, we take the sum of the sizes of the individual tensors of the individual lines in the proof. Now, here are the precise rules, but I don't think I think I was skip the precise details. As it turns out, this proof system can characterize as a tensor solver. So every run of a tensor solver can be transformed into a T-dense proof, and the other way around it also works. Every T-dense proof can be converted into a run of the tensor solver without too much increase in size. So it's all polynomial, so we can polynomial characterize our tensor-based solver. And now we can use all the techniques of proof complexity to talk about the solver. So, for example, we can ask about simulations. And we found out that the mice proof system simulates T-dense. So it's at least as strong. The T-dense proof system is as strong or weak as it will later turn out. It's weaker than mice, but the basic idea is that we can take a T-dense proof and convert it to a mice proof by looking at every tensor and every entry in this tensor and converting every tensor entry into a mice scale. So this tensor is associated with a partial formula, and every entry will become mice scale, and the formula of the tensor will become formula in mice scale. The position within the tensor will become the partial assignment. So here y and c are equal to 0. So we have the partial assignment here, and the tensor entry will become the model count. And if we do this, all the tensor operations become operations in the mice proof system. So the simulation works out. So now we already know that T-dense is not stronger than mice, but as it actually turns out, it's kind of weak in a way because it's characterized by the treeless of the formula. So there's a graph called primal graph associated with the formula. And we can look at this prerequisite column K, and then we can prove that the smallest T-dense proof always has a size exponential in K. And previously, in the case of the solvers, this was kind of an informal folklore thing that was already known. But through proof complexity, we can formalize it rigorously. And the idea is that we can take a T-dense proof and make a tree-like without substantially increasing its size. And these tree-like T-dense proofs are really similar to tree decompositions, which are the defining character, so which are used to define the treeless of this primal graph. So due to this result, we immediately can find lower bounds for the size of T-dense proof because we have these grid formulas. So we have a grid of variables, and adjacent variables are equal, and we make sure that they are equal with 2 clauses each for each pair of adjacent variables. And so this CNF has exactly 2 models because either the variables all have to be true, sparse systems can be exponentially stronger than the dense systems. Yeah, thank you.
The connection to clear composition, Lewis, and specifically is involved. In fact, is proceeding with BMC, this was already published a year earlier, and the model counter is based on clear compositions. So effectively, it derives conduction order of the clear composition.
Yeah. Okay.
I'll send you the pointer later.
Thank you. Thank you.
Yeah.
Yeah.
The technique you showed us seem to me just the good old sum of products which exists for 100 years as far as I know with a new name. Is there really something new to it?
I think so. What the fear seems kind of new to me is to bridge this gap because people in the physics community and other communities are always talking about these tensors. And so when I got started with this project, I'm not really active in these communities, so I didn't know about.
Couldn't it be that the principle just ignore this age-old constraint satisfaction?
So let's get started with a more popular problem, the problem of functional synthesis. So in case of synthesis, you have a set of input variables, a set of output variables, and you have a specification that says the relation between these input-output variables. So in case of Boolean function synthesis, the task is that you have a specification that is given as a Boolean formula over these input-output variables, and you have to synthesize a function that satisfies this specification. So that was the problem of synthesis. Now we are interested in the counting version of this problem. That is, given a specification, we want to know the number of functions that satisfies this specification. Let me give you an example. So let's say your specification says that the function should encode factorization. So the specification can be said in this way that if you multiply the outputs, then it gives you the input, and both the outputs are greater than 1. Now, given this specification, you can have different kind of function. For example, you can come up with a function f1 that factorizes 12 as 4 into 3. I can come up with another function f2 that factorizes 12 as 6 into 2. So the point is that given a specification, there can be multiple ways to implement that specification as a function. So let me be more specific that if we will call two functions as different if they are semantically different. That means that we say two functions are different if it is the case that they differ on outputting at least on one input. For example, if you have a specification a function that f of x equal to x and f of x equal to not of x, even though the functions looks different, we do not consider them as different functions because they have exactly same input-output behavior. Right. So the question is, why are we interested in these counting functions? So I'll give you two answers. So first one is more general, that when we are good at solving some problem, we look at problems that are harder than that. For example, when we become good at fact solving, we look into more expressive queries. Like we went for QBF solving, and we went for SMT solving, and so on. On the other hand, we also looked at richer queries. So that was the question of asking yes, no. We went for model counting where we wanted to know the number of satisfying assignments. So when we have this QBF or SMT, what is the quantitative question there? So this number of Scholen functions can be one way of quantifying the QBF formulas. For SMT, you have these uninterpreted functions. And in case of uninterpreted functions, if you want to know the number of uninterpreted functions that satisfies the formula, then this Scholen functions is one very restrictive class of uninterpreted functions. On the other hand, the second answer to why count functions is that they might have many applications in different domains. For example, like the count of the functions will give you an idea of how vague or how strict your specification is. And that will give you an idea of how diverse the specification might be. In the field of this specification engineering, where you have an engine and you want to know the specification of that engine, in that case, this number can be useful because that will give you a way to make the specification more tight or restrictive. So how hard is this problem? So theoretically, we do not know the very good bounds on it, but at least it is sharply hard. So possibly there is not a very easy solution to this problem. And more importantly, the common approaches that we have for model counting, that might not work here. For example, like in model counting, we have two common approaches that works pretty well. So we have this knowledge compilation based approaches while we want to make a succinct representation of the whole solution space. And the second approach is this hashing based approach where we partition the solution space and count a few models. So we do not know how to do any of those. We do not know how to have a succinct representation of all the Scholar functions. Also, we do not know how to do a hashing based approach in case of functions. And both these approaches are much harder than getting one solution. And in case of this Boolean function synthesis, the problem of synthesis itself is pretty hard. So enumerating all the solutions in some way is going to be much more harder. So what can we do in this case? So the approach we take here is we will be counting the number of functions without even synthesizing one single function. So how do you do that? Let me come to that. But before that, we have a small point that like the number of functions can be 2 to the power the number of input variables. So the number is very, very high. And storing that number itself is a pretty big challenge because it will take exponential number of bits. So we are just interested in the logarithm of the count. So let me go back to the question, how we are counting the number of functions without even synthesizing one function. That starts with a key observation on counting functions. Let's say you have a domain X of size 2. There are 2 elements, 2 and 3, and a range of what, that is 3 elements, 5, 6, and 7. And your specification says that the element 2 can map to only elements 5 and 6, element 3 that can map to any element. This is a pretty simple specification, and you can list down all the possible functions in such a way. And you have probably already figured out that the number of functions which is possible is simple. That is basically the number of elements 2 can map to times number of elements 3 can map to. So it is 2 times 3, so it is 6. You can generalize this, that like the number of functions, you know the number of functions, you have to look at every element in the domain. And for each of the element, you have to calculate how many elements it can map to. And if you multiply over all these numbers, you will get the number of functions. So if you look at the Boolean function specification, that specification is effectively a truth table. So you know for each element how many numbers it maps to. So you can easily use this function, use this technique to count the number of functions. And as we are interested in counting the logarithm, it is basically the summation over the log of range for each of the element.
This assumes that the elements are mapped individually with no constraints.
Sorry.
Take the product, we have to assume that each element maps independently to other elements. But we are given constraints.
Yeah, but you can think of that constraint as a truth table, right? That for each element, you know how many elements it maps to.
But it's an overestimate, it's not the number of functions.
But you know exactly how many element it maps to.
But I have constraints that say 2 and 3 can map to something that is constraints together. You have a constraint on each variable for each element here separately. What happens if you have combined constraints?
So can you encode that thing as a propositional formula?
I mean, here you assume that 2 has constraint and 3 has constraints. But what if I tell you that the value the 2 maps to must be less than the value the 3 maps? Then you cannot separate them.
Yeah, but when you look at the truth table, you know exactly how many elements they are mapping to. Right?
Okay, never mind.
Not in the normal, but in the Boolean domain, we can actually have it.
Then you're looking at not at the elements, but the sort of assignment. I see.
Okay. random variables, where the random variables lie between 0 and 1. And we have algorithms that runs by taking order of t by mu many samples and returns an estimate that lies between this epsilon, which lies between some epsilon found with high probability. And this t is a parameter that comes from epsilon as delta of this variable. Now, if we take our random variable like this, that lies between 0 and 1, so we can apply the Monte Carlo estimation methods to count this number of functions. So we have the algorithm that it takes all of t by mu many samples, but the problem here is we do not know the value of mu. The mu is the value that we are trying to calculate. And our random variable can go as low as 0. So we do not know how many samples we did. So can I get any guarantee on runtime? To do that, we have to do a small trick on the input base. So let's say that this is the set 2 to the s, the set of all possible assignment to the input variable. And we partition it into two parts. Let's call them S1 and S2. So S1 contains all those elements for which the number of solutions, number of elements it can map to is less than or equal to 1. S2 is the set for which the number of elements it can map to is more than 1. So now if you pick elements only from that we get from this Scholar FC that lies between this bound of epsilon with the high probability of delta. So we tried that algorithm on a set of benchmarks. We picked that set of benchmarks from this domain of synthesis. So we had 609 instances in that from synthesis domain. And we tried calculated calls or like any sample calls.
You're only going to be approximately.
Yeah.
So, we know of any QBF model counting systems, which I think they should be regularly based, right? Not make preparing calls.
Yeah, so there has been some work in like counting QBF formulas. And so the problem is slightly different because like we also count for unsatisfiable QBF formulas, they do not count for that. So the problem is slightly different. But there is one knowledge comparison based approach, and one is there is the enumerating models kind of approach.
You know what is the best they can make, like
Yeah, so we tried this that like the enumerating approach, and that one is set of instances, but that didn't solve any of the instances. So scalability is very similar.
So, when we synthesize function, there are a lot of pre-processing in that, like you calculate function, make functional modifications,
Right.
which basically comes into the situation like a range is less than one. Less than equal to one that you, so you identify that there are two cases where the range can be greater than two.
Yeah.
So did you try those pre-processing stuff or it was followed like CS?
Yeah. No, I haven't tried, but does it change the specification in some way or?
It will reduce, like, just like when you do model on, there are a lot of pre-processing things that you do in order to reduce.
Right. No. So my question is like, will it preserve the count?
Yes, yeah. At least that's what the first.
Okay. So I have not tried those, and that's thanks for the point.
Just like the model counters, you do a lot of pre-processing, right? Like the first model counter, so you can do a lot of pre-processing.
Right. Yeah. Yeah. That's a very good point. You should try that.
I have a basic question.
Yeah. Sure.
Mention 2 to the power 10 functions possible, right? So that is, if you have n variables, this is the total number of functions possible, but you don't have a specification which will reduce the.
Yeah. So I'm just saying that the maximum number of functions can be that much. So in practice, the number of functions can be much less.
So it is basically, so the example that you gave, for factorization, because different solutions are possible. So you're basically trying to find out not the ways we can synthesize a function, but how many functions with different outputs are possible.
Yes.
To specify this, satisfy this.
Yeah. Because like it can be the case that there is two different functions or circuits that have the exactly same input output behavior. So it's not differentiate that. And just to give you an example of how big that number is, so if I remember correctly, the number of ways we can like count the number of functions for, let's say, 6-bit factorization is possibly like 2 to the power 60 or something like that.
So the number of functions that you're trying to count,
Mhm.
any two functions differ on at least one input, right? For one input, the output will be different.
Yes. Yeah. So like that is how we differentiate functions.
Just a comment, I think it would be more clear if we say that we're counting the number of strategies.
Yeah.
Function is a strategy. If one figure function is a data, so the model count will be number of strategies.
Yeah. So that is not always true. For example, this for the factorization example, the formula is unsatisfiable because for if you have an input prime number, then there is no factorization. So yeah. So but not it is not that case for functions. So in like in functional synthesis, they say that like if you have a unsatisfiable formula and if you have some input for which there is no output, then you can output anything. So like that. So
We're saying the number of functions of statements. It's not.
yeah.
And why are we counting number of functions?
Yeah. So again, we can come back to this factorization example. Like you might be interested to know how many ways you want to we can factorize a number. Factorize like let's say 8-bit number. Like, there are how many ways are possible to have a circuit that factorizes 8-bit numbers. Right? But the function the specification is always unsatisfiable.
This wraps up our first session. We will reconvene at, after
Sorry?
Wherever you.
Yes, no. Okay, then. That's best. So, another announcement, is this take the same process, right? In this entity, student drinks are, so, please take the copy and,
For example, you gave the state five is a very confusing example.
yeah, and also, no photographs by your accepted TCS campus. This is a serious solicitor, huge company. Okay, yeah.
The values are.
ऑडियो फिक्स कर दो और उसको टच नहीं करने, राइट? अभी तो सेशन ब्रेक है ना? हाँ, बट सेशन नेक्स्ट